So the function that will print the tree is pretty straightforward. We're basically going to create a function which print the tree recursively. So we're going to call that print tree. And since it's a recursive function, then we're going to give it the root so that every time for every call, it'll change the calling parameter. It'll change the root between every call. Okay, so it'll take a root pointer, and that's it. Basically, we're gonna print this way. So if the root is null, it means that we're just gonna return. We're not gonna do anything, okay? Otherwise, if we did not return, then we're going to print tree on the left subtree, so that's root left child, and then we're gonna print tree on the right subtree, so that's root right child. Okay, and in between I'm going to just print f the value, so print f the value, so that's root value. And basically that's the function. So it'll make a bunch of recursive calls, and then it'll print, and then it'll return, and so on and so forth. So the order of printing will be like this. So it'll do it like this. So the function will call its left subchild, and which will call its left child, and then which will call its left child, and then its left child is null, then it'll return, it'll print this content, and then it'll call the right child, which is null, so it'll return, and then it'll return again, and then it'll print this content, and then it'll call the right child, which will call the left child, which is null, so it'll return, and it'll print its content, and then it'll call the right child, and then it'll return, and then it'll return again, and then it'll return again, and then it'll print the content of that cell, and then it'll call the right child, and then it'll call the left child, and then the left child, which is null, so it'll return, and it'll print the value of that that cell there, of that node there, and then it'll call the right subchild, which is null, so it'll return, and then it'll return again, and then it'll print the content of that node, and then it'll call the right child, which will call the left child, which is null, so it'll return again, and it'll print its content, and then it'll call the right child, which is null, and then it'll return, and then it'll return, and then it'll return, and then it'll return. So it'll print the content in that order, okay? So it'll print this one first, it'll print this one first, this one second, this one third, this one fourth, this one fifth, sixth, seventh, which means that it'll print the numbers in order, because we know the left you go, the more left you go, the less the numbers you get, the more you go right, the bigger numbers you get. So basically, if we print the numbers like this, we should print the tree in ordered manner. So let's code this idea, see if it works. And basically, it's a function of type void. I'm going to call this print tree, and the function takes a tree node pointer called root, and then if root equals null, so if root equals null, in that case we're just going to return. Otherwise, we're going to call the function with the left subchild, and then we're going to call it with the right subchild, and in between we're just going to print the value. So let's print f the value. So that's an integer separated with a tab, and then the element that we're going to print is the root value. And in this call, we're going to call the same function with the left child, and here with the right child. Cool. Let's compile, see if there's any syntax error. There's none. And now let's try to print the tree. So the function is called printTree, and we're going to give it the root of the tree. So that's troot. So let's compile and run. And as you can see, that these are the numbers of the tree in ordered. So that's 3, 4, 5, and 7. And as you can see, 7 got printed only once, which means that it's not duplicated multiple times in the list. Okay. If you want to change the order of the printing, all you have to do is to change this printf, for example, here before the first recursive call. So we're going to print the parent, and then we're going to print the left child, and then the right child recursively. Okay, so that's 5, 3, 4, 7. You can also make it here last after the second recursive call. And as you can see, the order of printing has changed. So the way the numbers, the values of the tree gets printed differently dependent on the position of the printf, whether it's before or after the recursive call, is called the infix and postfix and prefix method of printing the content of the tree. So now let's talk a little bit about the complexity of such a data structure. So if you want to add an element to the tree, whenever you want to add an element to the tree, you're basically on average traversing the height of the tree. The height of the tree, if the tree is balanced, then the height of the tree would be log the number of elements. So that's log the size of the tree. Okay, so if the tree has 124 elements, then the complexity would be log of that 1024. So that's 10 steps. Okay, because 2 to the 10 equals 1024. Okay, but of course this is if the tree is always balanced. What if we wanted to add these numbers to the tree? So 1, 2, 3, 4, up to 10,000. Okay, so the first number would be the root, that's 1, 2 is bigger than 1, 3 is bigger than 2, 4 is bigger than 3, and so on. So as you can see, all the numbers are the right childs of each other, which means that this has become just like a list, a linked list. So the worst case scenario of this, of inserting an element or retrieving an element from the tree would be order 1. Okay, it'll be order the complexity of inserting or retrieving an element from the tree. Okay, so the worst case would be n, so that's order n. Okay, but if the tree is balanced, then that'll not be order n anymore. That'll be order log of n. And of course, there are very popular algorithms that deal with balancing the tree, and among them, the most popular ones are the AVL trees, and there's also the red-black trees. Okay, there's a bunch of other trees, but these are the most popular ones. Cool. So basically that's it for this binary tree video. See you next time.